Okay, hello everyone. Good. Yes, so there is one last thing to finish our last lecture, then we go to Einstein-Hilbert action, so something that I find a bit more exciting. And there will be one semi-technical proposition, and after that there should be some quite interesting stuff, I dare to say, about Ricci flow and related things. Okay, so there is one lemma left over that we needed to finish the previous part. And this, I got a bit mixed up when I started writing it, but in fact everything was okay, not just write it again. So we saw fixed current algebra. So should I repeat this? No, so fixed current algebra. Okay, so now if mu is a density, meaning one density on M, let's assume this M was closed. Sorry, closed. So, which means compact and no boundary. So now we suppose that we have a density on M, and we have a section of the current algebra. And okay, if then for any generalized connection D, doesn't have to be Ricci or anything. We have the following thing: the integration of parts statement, which says. It's a different paper. So more or less, each time you see a d outside of, like, you have some integrand and you take the derivative of the whole of that thing, then the result is 0. Under the integral. So it's like integral of the total derivative is 0, it's kind of the unknown. And the proof is very direct. So we start and we calculate and we see that it's 0. So okay, so the role of this U is simply so that, you know, that, like, I mean, there was an index here, so it needs to be contracted with something. Okay, so using the product rule, what do we have? We have two terms there. We have, first of all, we can hit U. Now we get the trace of the connection hitting U. And then we have second term, where we have U alpha, and then we have D alpha of mu. But, okay, remembering the definition, so this is kind of, here I'm using the index scale version. So this is really the same as a covariant derivative of mu along U. Okay, that's how this thing is defined. And how does that work? So remember, we have a definition of how these operators act on densities. So it is the lead derivative of the anchor of the thing acting on mu, minus lambda being the density, so here lambda is 1. If it will be half density, there will be half. Then mu times the divergence of the connection. So this thing. This is how the connection acting on densities was defined. And now we see that this cancels with the second term, and the only thing that we have here is the lead derivative. And this is 0 because the integration operation is diffeomorphism invariant. So if you pull something along diffeomorphism, then it doesn't change the integral. So integral of lead derivative is 0. So there is that. So this just concludes the part that we did last time, which was about the self-adjointness of this Laplace operator. Okay. Come back to this paper, I guess. Okay, so with that out of our mind, now we can do some part. So we called it Einstein-Hilbert action. So maybe before doing anything, let me make a small recollection of what were the objects that we defined before, and which were the ones that were kind of good and which ones were the bad ones. So before we had so our data was this generalized metric, which was a map from E to E, and this was the same as splitting E into these two parts, V plus and V minus, in orthogonal splitting. So this was our analog of a metric variable, and then there was a sigma everywhere non-zero half density. Okay, so this was the data. This was the analog of Riemann metric, if you wish, in our context. And then for these things, we defined several objects. First of all, we defined Ricci connections. So those were connections that preserve G, preserve sigma, and are torsion free. And then we tried to cook up some interesting operators, curvature operators using D. And the procedure was kind of complicated, which I, again, feel reflects the fact that this field still needs to undergo some changes. But the way we did it, at least, one of the consistent ways that we did it is that we defined the Riemann object, of a Riemann curvature, which was bad, okay, in the sense that it depended on the representative D. But then we used it just as an auxiliary tool, and by further contracting it or looking at components of that thing, we ended up with two good objects, the Ricci tensor and the scalar curvature. And these were objects that indeed depended only on our original data, in the same sense as in the Riemann geometry you have the curvature tensors which depend on the metric only. I mean, in ordinary Riemann geometry you have this, this, and this. Here, good objects are only those ones. So if you see those things, then all is well. If you see this thing, then something is wrong, I would say. And then there was one more thing that we added, and that we studied with this Laplace operator, which depends on the metric. So this was kind of a mysterious object. So this is what we spent last the last part of the lecture. Okay, so now we will just kind of do the good stuff. So we will work with those things, except for one proposition which we need to prove to make it work. But so let's start with definition. Definition. So any current algebroid, which is the datum that we fix, we define the Einstein action, and it will be an action. So this is an action functional. It's an object which it's a function in the space of this data, generalized metrics and half densities. And we define it to be simply integral of the scalar curvature times sigma squared. Okay, so the only if you are given these two data, then the only thing that you can really write is this.
Wait, what exactly is this space of all metrics and half densities? Like, is it some sort of current algebra as well? It's
no. It's a so for any fixed.
But like it's a manifold, maybe. I'm not even sure about that.
You mean because of the size, or?
Yeah, like okay.
Yeah. No,
where does it go? Like it goes from some space to complex numbers, right?
For real numbers, yeah.
For real numbers, yeah. What is the space where it goes?
So the space is the space of all such pairs. So yeah, good. So let's remember. Okay. So
yeah.
Okay, that's right. So S is a map from product. So first generalized metric. So generalized metric is a vector bound endomorphism, satisfying the property that if you square it, it's 1 and it's symmetric. And there was this one unfortunate technical tool that I said at some point we will assume that the eigenbundle such and such will have rank different from 1 or something. But you feel free to ignore that. That's just okay. Yeah. So let's just say this is the definition. This one. This is the space of generalized metrics.
Yes.
And then there is space of sigmas, and that's simply that's sigma of Hall densities. I think we call them L1 of. This is the line bundle over M.
Yeah.
Hall densities. And the thing I require is that sigma everywhere 1, 0. 0. So, and we know that for any point in here, we can define this thing.
Yeah.
So this thing is a function. This is a function of the base manifold. This thing was not. This was a section of some bundles. B plus tensor V minus. Yeah. So for such pair, you construct the scalar curvature, which is a function of the base manifold. Then you multiply it by sigma squared, the density, and then integrate.
But this S, it's just a set. Like no extra structure, we don't care.
You mean this thing, the
Yeah.
domain? Well, yes and no. Well, as I roll it up, I mentioned, yeah, it's just a set. But soon, I don't remember how soon, later on we will also see that a sort of, big manifold.
Okay, it's a manifold. Okay.
Well, it's a manifold of sorts. I don't know. You have to. I'm not a big expert on infinite dimensional manifolds. So you have to. I don't know. Put some appropriate topology on it or something.
Oh, it's infinite. Oh yeah, the second part is okay. Yeah. Maybe even the first one. Yeah. Okay.
It's not a linear space because none of these two factors are linear, but it's like, it's very non-problematic.
Okay.
Okay. Note that we need both things. Like for general current algebra, you just can't define this thing. Well, you could define using sigma. I guess you could just say that it's integral of 1 times sigma squared, but that's kind of boring. That's kind of like a cosmological constant. Kind of sorry. Okay, so my statement was false. You can do something with sigma only, but it's boring. Okay, so you should compare this with. You have in like ordinary Riemann geometry, you have a metric, and you have the Einstein-Hilbert function, which is that you take the scalar curvature for that metric and you multiply it with the metric volume form. So this is what you do in Riemann geometry. Now the big change conceptually here is that now we treat this thing as a separate variable here. And also this function now also depends on it a little bit. Slightly more subtle, but it is what it is. Okay, so now what we want to do is that I want to and also before we introduce that Laplace operator, so let me write here for comparison. So minus. It's an unfortunate factor, but this thing you can actually write it using that operator, that Laplace operator. Which is somewhat, this is kind of nicer for some functional analysis properties. It's like you have some nice self-adjoint operator here. Elliptic. Okay, so that's the definition. So now the thing we want to vary this. So we want to see what are the equations that what are the external of this, or even better, what is the gradient flow of this? So we'll get to that. And we will see that this Ricci tensor pops up. Probably not many things that can pop up anyway. So the first step to that is, and this is the only I think technical lemma that we will see. Everything else will be just very easy. But even this technical lemma carries a name, so I think it's probably more interesting. This is another what is called a Palatine identity, I think. Someone can confirm. I don't know this nomenclature as well. Palatine identity. I think this is how Wikipedia calls it. So, so under a change, so this thing tells us how do the curvature tensors change if I change the connection. So, under a change of the torsion-free connection, so if I start with a D and I change it and I add something to it, We call this something A. So under this change, the way the Riemann tensor changes. Okay, well, this is just delta of Riemann, so the way Riemann changes. Don't ask me why these Greek letters. I don't know. I just copied it from somewhere. Okay. So this is the first thing to know. The hardest, I guess. And now, if you carefully remember how I defined those tensors, then I defined them for Levy with the connections, but in fact, okay. Let me recall how Riemann was defined. Yes, okay. Okay, you can do it. Riemann for a connection. Actually,
you know what I don't know. Maybe. I mean, the proof is there. It's a calculation. You take that horrible formula and you punch it until this thing falls out. It's not terribly enlightening. So I don't know. Maybe okay. Would anyone be very much against if I skip the proof?
you will take it.
No, skip it.
Okay.
It's really. There's nothing else about happening. You have to figure out how each of the terms transformed, and it's like I don't know, a couple of lines.
So yeah. So the
Sorry, can I ask you?
Yeah.
something? Just to be sure about the meaning. It's like this is delta of Riemann, like this is a change.
yes, that's the change.
And then the stop indices.
That's right. So this is Riemann of this minus Riemann of the.
Yeah, but
And the indices, yeah.
what is this one? Is it like?
Why is there? So Riemann is for Riemann is an element of Riemann tensor, just like in ordinary geometry. It has four indices. In this case, it's an element of the fourth tensor power.
But this subindex is just this. I mean, it's just confusing. Like it looks like a delta. So
Oh, this one.
it doesn't.
Well, this is delta. Yeah, it's a different. This is a small delta. This is a
Oh.
subscript.
Yeah,
Yeah.
I mean, I'm just asking because maybe it's something else.
No,
Okay,
I'm
yeah.
sorry. No. Also, I'm sorry about the way I've written it. I know that this is how it needs to be in my notes. It's like it doesn't follow any obvious rule, like this ordering of Greek first four Greek letters. Yeah, no, it just means that you take the delta, gamma, alpha, beta component. And
Yeah.
like this.
Okay.
If you know, they look at like the of gamma and delta. It could be this a little bit more appropriate. But okay. Yeah, no, sorry, there's nothing deep there. Maybe one thing is that before, okay, so, okay, so here we take Riemann D defined for any torsion free D. So I looked back at the notes of how I presented these things, and at the beginning there was this tensor, and I defined this specifically for Levi-Civita. But in fact, if you look at the definition and on the properties of that thing, this thing doesn't carry. The only thing you really need in order for the propositions we had to be true is that this D was torsion-free. So I should have emphasized that maybe, but I forgot to do that. So everything stays the same. The only way you use the generalized metric and sigma later on is that you do. Well, okay. The statement is still true. Like this object is only defined based on a connection D, and then you do something to either contract it along some directions. That contraction depends on G here as well, because you contract with G and whatever. So, but this object, at the very least, it's just something that can be constructed using a connection and nothing else. And here we are expressing how it changes when you change the connection. So yeah, that's all there is to it.
And now that we have this nasty part out, then we can do some more exciting thing. Let's see. Unless there's questions, let me know.
Yeah, it's just like linear part of the variation.
No, it's the full part. Yes, so the good question. So the way this looks is that there is like some. So this thing is a linear. This thing is an expression that. Okay, there is an image that I hold out of the expression. It's long, I won't go into it, but the expression is linear in all these things, and it contains the operator t twice. So there's like some sort of d squared, and then there is some w, z, x, and y flying around. You're hitting them and whatever. So if you vary, oh, I see what you mean.
I mean a square actually.
Uh,
Like
oh.
in principle there should be some a square, right?
You're right, yeah. Wait, what?
I think in my thesis I have a square.
Okay, yeah, then you're. Then what did I mess up? Sorry. You're right. I haven't even read my own proof. Yes, this was an infinitesimal variation. Okay.
So it's for epsilon a, where epsilon
Yeah. Yes. So. Thank you. Yeah. There is still this. There is a square term. Okay. Yeah. Okay. Thanks. Under infinitesimal. Yes, that's it. Yeah. That's all that we want for the variation, but very good. That was that's very good. Okay. Any other questions or mistakes spotted? Okay. Then let's do something that I would generally call a theorem. So under the variation of G and sigma. Variation usually means here like infinitesimal variation. We have that the action functional changes by the following quantity. Okay, so by variation I mean that G goes vary slightly, so I change it. And this goes to sigma, this goes to sigma. Okay, this is contracted with Ricci. And then sigma squared plus 2 times r times sigma times delta sigma. Okay, remember that the indices, this has Latin indices and this thing has Latin indices with the dots. So, but both of these standards, they only have b plus and b minus parts. So if you don't like indices, you can just say that I pair these two things together. And I think this one is slightly less confusing because you don't double count some things. Okay, and now the proof of that, now that we've established all the important bits, now the proof of this itself is kind of nice. So, or maybe before the proof, let me remind you that, let me elaborate on what I just said. So if I, remember that if I have, there's this claim that delta G, okay. So suppose that I have a generalized matrix. Generalized matrix is something satisfying these properties. I did a similar calculation before, but let me repeat it. So generalized matrix is an endomorphism which does have these two properties. Now if I vary it, so if I change it, and I want that this new object still satisfies these properties, then what does it tell me about this change? Where does this, seeing both as an endomorphism, seeing G as an endomorphism, I change it by a small endomorphism. Now what are the conditions on this endomorphism in order that these two things are satisfied? Well, the second condition tells me that delta G has to be symmetric as well. Okay, so this has to be symmetric. What about the first condition? That's a bit more slightly trivial. So first condition, if I just apply variation delta on this, what do I get? I get delta of GG is the variation of 1 is 0. So if I make a variation of the thing, then I get this, and spelling this out, this is this. So it tells you that G anti-commutes with delta G. Which is still maybe somewhat difficult, so let me write it in indices to make it easier. What does this thing say? It says that. Maybe I can do it without indices. Well, I prepared it. So, so now the question is that you know how G looks like. G is a thing that on V plus minus it is plus minus identity. So let's I take gamma, the Greek index gamma to be one of the two, so I take it to be in V plus. So it's really, yeah. So if this is in, what do I get? So if this was in V plus, it means that, well, this thing has to be G restricted to that V plus is an identity, so this becomes Kronecker, and I can sum it up from the first term. I just get this one. Let me say, okay. I think I'm overcomplicating it. Okay, let's. Okay. Let me try to do it directly. Okay, so let's suppose that I take a. What I want to. Okay, you can help me out. What I want to say is that if this is a thing that it maps V plus into V minus and vice versa. This is what I want to show. Now I established how to show that quickly. Yeah, okay, so let's take that. I take V plus, a section of V plus. And then I apply the left hand side on it. And I know that it's 0. So delta G on G on V plus. Plus G delta G on V plus 0. Now G on V plus is V plus because G is an identity on V plus, so this is V plus. And then I have delta G on V plus, so this thing gives me 1 plus G on delta G on V plus 0. Right? V plus delta G, first term, this is the second term, and so this is this guy is up to 1/2 in there. That's 0. This thing is the projection onto V plus. And this thing says that if I take something in V plus, act with this operator on it, then the thing projects to 0 on V plus, which means it has to be in V minus. So this thing has to be in V minus. So this thing means the delta G on V plus is in V minus. And you can do the same if I would put a minus in here. Minus, and this thing is plus minus. And here I put a plus minus. This is the operation to the V minus, so this thing shows both. Okay.
And the symmetric part comes from the subhomogeneous.
Yes. Yes. So the moral is that the only the only non-zero part delta G is delta G with this kind of mixed this one and corresponding to this one, but they are the same because of symmetry. Okay, so the thing to remember, I guess, is that there is this space of these mixed things, and this one is important because two things live in there. First of all, Ricci tensor lives in here. If you remember, Ricci was defined to live in there. That's how we define it. And this thing also shows you that that thing is the only non-trivial part that variations can have. So this is the tangent space at tangent space to the space of generalized metrics at G. Okay? That's what we just established. And if you sit at a G and you want to deform it, then the only thing that you can add to it is something like this. It has two parts, but they are the same. So essentially, information is just hidden in this kind of fixed thing. So, okay, so yeah, that's where these two things meet, and that's how Ricci form works. Ricci tells you how to deform this thing. Ricci gives you a vector at the space of metrics. Okay. Sorry, it was a bit of a digression, just to partly explain why these two things are constructed. Okay, now let's do it. Okay, any questions? You have good questions, so please keep. Even if they are not good questions, it's always better to ask. So let's continue here with the proof. Okay, proof is very short. As all good proofs go. So, what do we have there? We have a scalar curvature. Here is the definition. Okay. We call that this thing was R times sigma squared. Now, one way to access this R was that it was a contraction of the Riemann tensor. So we defined it in some way, and then we said that actually it's the same as if you do it this way, because gamma. It's a contraction of Riemann on some two indices, but not quite. There was some unfortunate thing, but this thing, as we showed, as we said, this is independent of G, sigma, D, of everything. This is just some mysterious function. On a current algebra, we don't care about. It's independent of all these variables. The important thing is that scalar curvature morally is a contraction of Riemann. Okay, so what happens now if we vary the scalar curvature? So in ordinary geometry, if you vary scalar curvature, you do it by varying your metric. That induces some change on the connection, so your limit with the connection changes. And then you just use this path in the identity or whatever to see how the curvature is going to change. Unfortunately, there is no unique Levi-Civita connection, so we cannot follow this thing. But okay, let me first write variation of this and then. I vary this, so I first vary this thing. And then we have a variation of the Riemann tensor. Okay, I'm wondering if I. Okay, let's see about this. So, okay. Okay, so you might remember that there was this statement before when we were talking about Levy-Chita connections, and we said that they are not unique. But there was at least something that we could say, like when we were trying to construct a Levy-Chita connection to show that they exist, and there was this kind of algebraic, we had some formulas and there was some big map between some representations, and we said that this actually is surjective or whatever, we can find an inverse that goes the other direction. So following that argument, yeah, I didn't realize that I needed here that much, but anyway, like following that argument, you can show that there is a okay. Sorry, let me wrap this as a claim. So fixing G and sorry. So suppose we have a family of such things, and we have one Levy-Chita connection at the beginning for the time zero. Then there is a natural family, canonical maybe that's the word, canonical family of Levy-Chita connections that keeps being Levy-Chita along this thing. So although given a metric and sigma, there is many Levy-Chitas. Turns out that if you have a family and you have one Levy-Chita connection, then there's a natural way to vary it to produce a family. So there is no and I mean the proof of this fact is essentially the thing I just gave there. Like you have a connection and you want to change it. You know, like you are sitting at time zero and you are moving to some epsilon time. You want to change your connection. So what is the change of connections? It's a tensor. The difference of two connections is a tensor. So you need to add some sort of tensor quantity to it. And that's easier. Well, the thing you do is that sitting at that point with that generalized metric, you can that tensor that you're interested in adding, you can decompose that into representations of the orthogonal group or something like that with respect to the metric. And you can play with the representations, and you can see that there is like a natural candidate that you can put in there. So there is nothing terribly deep behind this. It's just like representation theory of compact groups or something, and some very simple disguise. So this is not a hard theorem. I thought that it follows directly from what I said in the other lecture, but I think maybe it requires a little bit more thinking. But it's true nevertheless, and it's the same argument. This just follows from the fact that.
Sorry, in what way it's canonical? Like,
it's canonical in the sense that I can write a formula for it. In that sense.
And it depends only on G0, sigma 0.
Yes.
Well, no, it depends on Gt and sigma t.
Yes. Yeah. There is a better way to say what it is.
So maybe I had another question.
Yeah.
Is it unique also, or just...
No. They are never... Sorry?
yeah, no, I was pointing to this direction.
No.
When you say canonical, then usually there's some criteria and you can choose it somehow, not just you can write the formula. It's not usually what canonical means.
Yes. So, but it's still like but that's the sense in which I'm. I mean, the fact that there is a formula for it means that it's something. Maybe that's a natural is more appropriate. Yeah, let me uncross. Natural is better. It's a thing that doesn't involve any other
So you
choice.
can like write it easily somehow.
You can write
the
it.
data.
I would not
can
say-
explain what it should be.
Except not, I would scrap the word easily. It's not that easy, but there is a. Yeah. But
And do you have the formulas on your papers?
yeah, it's in the Ricci flow paper, for instance. I even at some point wrote it out to myself in full, but that's kind of stupid and should not have done that. So the better way to say this, if you want, this was pointed out by Marco Gualtieri. Better way to say this. So we have this big space, the one that you asked about, so this space of space of pairs of G and sigma. This is an infinite dimensional space where each point is represented by a metric and Hall density. And for each set K2, we have a family of Levi-Schmidt connections. So there is a bundle. So this is a bundle. So I don't know what to call it. Levi-Schmidt connections. That's how we call it. Levi-Schmidt connections form a bundle over this because I need to tell you. For each G and sigma, I have a fiber, which is the corresponding fiber of Levi-Schmidt connections. This is an affine bundle. It's not a vector bundle because connections form an affine space. So this is an affine bundle. Okay, it simply means what I wrote. Like this is a space that at this point here the fiber is given by the Levi-Schmidt connections for that thing, which is a big space. It's infinite dimensional or whatever. And the claim is that this thing has a natural connection on it. That's what that means. So if I
So it's like relief of the curve in.
Yes. Exactly. It's a little bit curve once you specify starting point.
Yeah. Okay. That's it.
This has a natural connection. And that connection only really uses Lie representation. Like, I'm making it sound complicated. It's not a very it's once you write it down, you will see for yourself. I don't suggest you do that, but like, yeah. Okay, yeah. So probably there's going to be lecture notes which are maybe happening. When they are happening, maybe I will include that as well. Okay. Anyway, all of that is just to say that I can do that. I have a variation. I vary this thing, so I can also naturally vary my Levi-Schmidt connection, whatever I took it to be. So this thing will just be that formula above. So this will be some like dA. Let me just say like this. It's that formula above, but we won't even need the full fact, just that it's d of something. Okay, so. Yeah, and this A was coming from there. Okay, sorry. Is that okay? I had my G. I varied my G a little bit, varied my sigma. So now pick any. I guess we should have picked the D. Okay. By this proposition, I can vary D in a natural way. Hence, I can plug it into the Riemann in that formula, and I get that this is the variation of R. Okay. Okay. Well, that's it. Because now.
So I'm sorry, I'm a bit confused.
No,
Shouldn't
please.
Shouldn't it be something like dA times delta G? Like, no, that's the
dA.
no dA is just that time, but there should be like a delta G.
Oh, the A has the A is a change. A is delta D.
Yes.
So delta G has delta. Sorry, delta D has delta G in it.
Oh, okay.
So, yeah. So essentially, what this big arrow says, it says that delta D is some horrible expression applied delta G and delta sigma. Linear in those things. So horrible expression delta G plus horrible expression delta sigma.
Okay.
Thank you. Yeah, yeah, that was confusing. Does it make sense now?
Yeah. So dA is still a
Is it
vector. Yeah, like a vector.
Yes. Yes. Yeah. It's the yeah.
Or half of.
Yeah.
Okay.
It has a delta.
Yeah.
No.
Thanks.
But the reason I'm not writing it explicitly because this term will not contribute. For the reason that I want to integrate this. And so what is this term? So first of all, there is a G here, but we know that D preserves G. So keeping the question marks there, like we will get some sort of like D, and then we have some G and A, and there will be some indices, whatever the indices are. Doesn't matter. It will look like this. And hence, in the in here, this thing will simply. Okay, so in it will vanish under the integral, as you will see. Let me first address this thing. So we know that delta G, the only non-zero parts that it has are the mixed ones, plus, minus, and minus, plus. And it's symmetric. This one is also symmetric. So I can just reduce this thing to 2 times delta G A C dot, Riemann of beta A beta C dot. Yes. And then if you remember how this is precisely the Ricci tensor up to the factor. So this is 1/2 of the Ricci tensor A and C dot. So this is the reason why I drag us all the way through the Riemann for this one proof. So that to show that if you vary the scalar curvature, then since you obtain both this guy and Ricci as contractions of Riemann, this is why they are linked in this variational formula. This is how one becomes the other. Well, namely, yeah, in this term. Because this thing has a contraction. Yeah, I mean, this is how you get Ricci. So, well, the corollary is that now if I look at that and I plug it in, so what do I have here? I have 1/2 of 1. That cancels. So I have delta G AC dot times Ricci AC dot times sigma squared. What did I mess up? Oh, nothing. Yeah, sorry. Yeah, this is the. Sorry. This has 2 terms, right? I mean, this is the. I need to vary R and I need to vary sigma. So. Oh boy. So this is delta R sigma squared plus 2R sigma delta sigma. Okay. Now this first term is what I wrote before, so this is integral of delta G AC dot Ricci AC dot and sigma squared. And now this other term is whatever this thing was multiplied by sigma squared. But D preserves not only G, preserves sigma, so I can just as well put sigma here, and then I can use my integration by parts to say that this is 0. Because, of course, this is compact. And that's what I wanted to prove. It's the variational formula. Okay? So this is the point which is kind of subtle, but I mean the implication of this is subtle, but it's very important. It has deep consequence, and that is the fact that you get a Ricci directly. If you would, for instance, fix sigma, and if you would not vary sigma, then you would get Ricci on the nose, which is not what you get in GR. You get the Einstein tensor. Okay, that makes sense. Okay, great. Okay, and now we can even go beyond, and now we can talk not about. So one thing that this shows us is that so in particular we know what the critical points of the Einstein-Hilbert functional are here. Well, they are simply the points where there is a formula, but the delta S is this plus this. So the critical points are the ones where the coefficient of this vanishes, so scalar curvature is 0, and the fact where the coefficient of delta G vanishes, namely the Ricci is 0. So the critical points of the Einstein-Hilbert functional here are the vanishing of the generalized scalar curvature and the vanishing of the generalized Ricci tensor, which are actually two independent conditions. One doesn't follow from the other in generalized geometry. Okay, but we know more. Not only we know what the critical points are, we know what the variations.
So we can do some more fun stuff with it. We can define.
Okay. Name. No, okay. Because definition of this more of a notation. So we will consider the following space, let me just recall. So the space which is generalized matrix times everywhere non-zero half densities. Everywhere non-zero half densities. So this is the space of our geometric structures that we're studying. I could have even picked a name for this, but this is the only time that I'm going to write it up, and I will just not give it a name. So on this space, first we have a natural metric on this. So we define an inner product. And I should say that, okay, maybe at this stage, I should, if you want to interpret these statements correctly, one should probably be careful because it's an infinite dimensional. I mean, I want to define inner product, so I want to treat it as a manifold. I want to look at the tangent spaces, but it's all fine. It's just let me ignore all the nuances right here. And so I will define the. Okay. So what does inner product means? It's something that inner product of this is it eats two. Therefore, it eats two vectors and produces a number. Now, what is a vector here? It's a deformation of. It's an inner product which depends on the point where you are, because it's like a manifold, really. Like, depends on which point you calculate it. So you sit at a point g and sigma, and you want to calculate it. So you need to look at two vectors here. Now, what is a vector in here? It's a deformation either of this or this, which I will simply call delta g. So if I have two different deformations, or even let me do one. I mean, we can. Okay. If I take a delta deformation of a generalized metric, then I declare that its inner product with itself is now what's the coefficient? Minus 1/2. I'll just pair them together. Times sigma squared, because I need to integrate the density. Okay? If I have two variations, two infinitesimal deformations of metrics, so two tangent vectors to the space of metrics, I can simply, they are sections of some bundle, so I can just contract them using the pairing and then integrate. And similarly, if I have two changes of the, if I have a change of the half density, then I can do even easier stuff. What? Minus 4. Okay. Minus 4. Okay, and the last thing I'd say that these things are orthogonal. Okay, I'm not telling you what the inner product between arbitrary two vectors are, but I'm just telling you this, and from the polarization formulas you can deduce what if I would have two different variations, then essentially, if you plug it in, essentially there would be one variation here and one variation there. Okay, do you agree that this is all that you need to calculate the inner product on this space? So this thing tells you that all directions here are orthogonal to directions there. That's what the last thing tells you. It tells you that the inner product on this data is constant. It has constant coefficients. This integral does not depend on g and sigma. It only depends on delta sigma. Okay? So this thing is constant in the sense of But this one does. This one involves sigma. So it's really some sort of, I don't know, warped product of Riemannian spaces or something. So one Riemannian space which has a metric of its own, which is constant, which is this. And then you multiply it with another one, and then you define a metric on this guy, which depends on where you sit on the second factor. Anyway, it's the only thing you can do if you think about it, up to the coefficients. The coefficients you can, in principle, change.
So it looks symmetric, definitely, and possibly non-degenerate, or is it a metric?
Oh, yes. It's not positive opinion.
No, it's okay, yeah. You have minuses,
But I mean, it's as close to a metric as you can get in an multi-dimensional space. So it's like,
Yeah.
if you, it doesn't have any obvious cardinal like.
yeah.
But because the pairing here that you're using is not non-degenerate, so it has all the properties of a metric, except not positive definite. Not positive definite. And very because, well, this thing is always negative. This thing is also clear because typically the pairing here on these indices is positive and this here is negative, so this thing might be positive, that's fine, but this one is definitely not.
Yeah.
You might think, why don't I change this? Oh?
But also who cares?
Well, that was a bit harsh, but
No, not for
no, I know what you mean. Yeah, it's not. It has some. This is related. I think this is vaguely related to the fact that when working in string theory and looking at like string versus Einstein frame or something, and then one of them, the scalar, the dilaton has the wrong sign of the kinetic form or something like this. There's some physical thing behind, and let me not go into that. No. But let me make the more exciting definition. Let me have the define Ricci flow. The definition. The flow of gradient of the Einstein-Hilbert functional is called the generalized Ricci flow. Okay, so to reiterate, generalized parentheses again because it's the only flow that we'll see. So we have this space of the structure that we're interested in, the generalized metrics and the Hall densities. We notice that there is a metric on that space. We have also a function on that space, so right, the Einstein-Hilbert functional was something that lived here. So we can, if you have a function and a metric, then you can calculate the gradient of that. The gradient is a vector field. And now I just call that the generalized Ricci flow. Okay, so this is the big space of all pairs of G and sigma. We have a metric there, and we have a function, and well, this is the gradient S. Now let's calculate it. I mean, we have formulas, so we can see explicitly what this thing looks like. Why is it called Ricci? Like, what does that have anything to do with Ricci? Or maybe Ricci was the first who studied it, or I don't know. Yeah, it seems that people are thinking, so let me erase this again. And please ask. The thing to remember is the formulas I erased anyway, so the variation was set of S. No questions? Okay, so let's calculate. So, so how does one calculate the gradient of something, especially when it's something infinite like this? So, what is the property of the gradient of a function? So, if I have a gradient of a function, what does gradient mean? It means that I apply their differential to a function, and then I use the metric to invert the metric to bring it to a vector. In other words, it means that if I use the metric to pair this thing with a vector, then this is the same as pairing a vector with ds. Okay, ds, which is the same as v on s. Okay, v is a vector. Okay, gradient is a thing such that if you use the inner product to pair it with any vector, then that gives you the action of that vector on your function, the change of the function under the vector. Okay, so what is our vector in this case? On that big space, well, we said that the vector there corresponds to a deformation of G, and it corresponds to a deformation of sigma. I can write it like this. Okay, so now let's calculate the right-hand side, and let's see if we can bring it into the left-hand side form. What is V of S? Well, what does it mean? It means I'm differentiating function in the direction. What does it mean? I evaluate my function along that curve, and I differentiate. Well, but that's the same thing as to say that this is what I would normally call delta S. This is the change of S under G goes to G plus delta G, and sigma goes to sigma plus delta sigma. Which is precisely what we calculated in the previous theorem. So what was the result? This was integral Ricci a c dot delta G a c dot sigma square plus 2r sigma delta sigma. Okay, now can I write it in this form? Well, I almost can. I have that in the product. So, how should I write it? I guess my notes. It should be this one. Okay, this should be the above expression. Let's see. So this is inner product at the point where we are sitting. So G and sigma. So does it work? In the first case, I have a minus 1/2, which fills this minus 2 and lines up precisely with this thing. And in the second one, I have minus 1/2, and I have minus 4, which gives 2. Okay. Does it work?
Sorry, I'm a bit confused on the use of V. So I would see delta S more as just ds. No V involved, you know.
Yes.
But the D on the space, on the function space of.
Yes. Okay. So this is a more of an. Okay. Yeah. You're right. So. Okay. So. Yes. I know. Okay. So maybe it would be better to, instead of this one, say the delta S paired with V. That would fit with what you are saying, right?
Yes.
But what I'm saying is that there is two meanings. Okay, yeah, I shouldn't have been confused. That there is two ways what you mean by delta S. One of them is that you just it's a one form, as you are saying,
Yeah.
which in this case has this value, where now this is the one form and this is the one form.
Yes.
That's what you would mean. What I meant here is instead was that I now perform these variations in a specific direction. So for me, those things are already like functional. They're like, so I'm contrasting with this V.
Okay.
So I already evaluate
The component functions of V.
Component functions of
V.
yes, yeah.
Okay.
So here okay, sorry. It's a mixture of two languages. I shouldn't have said that, but here I meant it in like a more down-to-earth language, saying that simply what if you vary something under some changes by some explicit thing, then that's what I mean.
Right.
Is that okay?
No, it's clear. Thanks.
Yeah, good. That's, thanks for pointing this out. Okay, so now we can just extract this thing, and we see that the gradient of S is a vector. It has components along that part and that part. The component along the first part is minus 2 Ricci, and the component along the other part is minus 1/2 R. So, oh, sorry, M sigma. So generalized Ricci flow. If I will now imagine that I have really a flow of some families of such objects, so then the equations for that are this thing is minus 2 Ricci, and the change of the sigma is minus 1/2 R times sigma. Okay. This is called the generalized Ricci flow. And you see that why it's called Ricci, because there is Ricci there.
And so now what does this have to do with the gradient of this? So you are saying that these are...
The gradient of S is this.
Okay.
Because I define Ricci more kind of...
Also these are like the integral curves?
yes. Yeah. Here I wrote the integral curves, but the kind of important thing is this one, that the gradient of S as a vector field is this.
Yeah, makes sense.
Then if you want to flow elongation, this is the thing. Unfortunately, yeah, I mean, this is a PDE, very nonlinear one, so it's not even clear if such a thing exists, even for like a short time, because it's a complicated 3D question. So at the moment I'm kind of ignoring that sort of thing. Like for instance, famously, because this is supposed to be sort of like a heat equation, a nonlinear version of a heat equation. If I would, flip the sign here, then you know that you shouldn't flip sign on the heat equation. It's bad, because then it doesn't. So there is like, it's subtle whether this thing works or not. Claiming that it works under some positiveness assumptions, but that's for later.
So the version of gradient is once you kind of raise the index by the metric on that space already? Or?
You see, so gradient, definition of gradient uses the metric,
Okay.
right? Gradient is d of the function and then inverse of metric applied to it, so it's a vector.
Also this is already a vector. The
Gradient is a vector, yes. Yeah. Gradient is like g inverse of the thing.
Yes.
The way the metric appears is in this round brackets. I just found this one to be the convenient way to write it. Originally I did it in a different way, but this one is much more transparent. Is it good? Yeah, but please tell me if there is anything. Those are very good questions. Yeah, so okay. Otherwise, I wanted to say something about the coefficients there, because that's kind of an interesting thing. So why those coefficients? So why minus 1/2 and minus 4 in the definition of this thing? So, well, first claim is that the overall. So what would happen if I would rescale them? So the overall coefficient is kind of irrelevant. It would just mean that you rescale the metric with something, and then it would just mean that these things get rescaled somehow. But that would just mean that you're flowing faster or slower. It would not change the geometry of the flow. So the overall, I could multiply them by the common factor, like 7, if I wanted. This is, as you see, this is kind of a compromise to get them as close to identity as I could. Okay, so what about the relative thing? So, well, it turns out that this thing has a semi-physical. So the relative factor. This is a remark for the expert. So the relative factor. So if I would fix one and change the other one, then this corresponds to change of the randomization scheme. So the relative factor corresponds to the choice of randomization group scheme, because I forgot to say, this thing is the renormalization, incidentally, renormalization group flow of the 2D sigma model in a target given by G and sigma. Okay, this is an aside for experts. But in physical, these equations have the meaning of being the renormalization group flow. And as always, in calculating such things, sometimes there's a little bit of freedom in choosing the scheme, because this is some complicated thing. And the choice that is here, I understand, corresponds to the dimensional regularization. So this choice, this particular choice corresponds to the dimensional regularization, which is one of the most popular ones. Okay, for more details, see Polchinski's book on string theory, volume 1. Okay, this is just to throw in some fancy word. Okay. Okay, good. I think we are. I won't get to the most interesting part, but I will get to the semi-most interesting part, and that's a good point to stop. So there is one thing that. So as I said, there is some things in generalized geometry. In generalized geometry, you have less things to do because only some objects make sense. Like Ricci, it's scalar curvature. Riemann doesn't. The Einstein-Hilbert functional makes sense. It somehow suspiciously things that do make sense seem to be connected with string theory in one way or another. That may be a good thing to keep in mind. So, what other things do we have in ordinary Riemann geometry? Well, there is some, for instance, there is the famous Bianchi identities. So there are some identities on the curvature tensors. But as we said, Riemann is not really so the Bianchi identity in general, in Riemann geometry is some identity on Riemann tensor. Riemann tensor for us is not a great object, so we should probably not expect that to have some good Bianchi identity. But in ordinary Riemann geometry, we also have a tower of Bianchi identity. That's just too strong of a word. You can contract the Bianchi identity to get some Bianchi identities for the contracted tensors, which are Ricci and scalar curvature. And if you contract them enough, then there is even an identity that links Ricci and scalar curvature in ordinary geometry. Some differential Bianchi identity. So that you might hope exists here as well. And it does. So that's the last thing. And the way to, an elegant way to prove that even in classical case is using the Einstein-Hilbert functional. So so let me show that, and that's that, and there. But before that, I will need a lemma. So if you remember, some time ago we had a formula for what this thing was. So if you take the lead derivative, a generalized lead derivative of the metric, and there was a formula for this thing in terms of brackets on the current algebra. And there's a different formula which says that if D is a Levi-Civita connection, then you can write this thing as -4 This is somewhat similar to what you have in ordinary geometry. You have this kind of the way the derivative of metric you can rewrite in terms of covariant derivatives, and you get this kind of famous killing whatever related expressions. So it's not that alien. Yeah, let's show this. So remember, one of the conditions of Levi-Civita was that it's torsion free. And what does torsion freeness means? It means this. Now, what will I do from this is that I will now use this to get a handy formula for what this thing is. Okay, because again, this term here, this is the derivative of v along here, generalized. So I can express the derivative using the connection by simply erasing all of v. Okay, so what I get, it's, if I put this on the left, I get that this is v of d with respect to u. And then I have this one, so minus d of u. And then I have this one, which I will call v u transpose. Okay? Explanation, what does this mean? It means that those two things, this is transpose, this is something, this is a linear map, okay? Yeah, I'm just trying to rewrite this formula differently. Now I do that by erasing v, but then I have to explain what I mean. So the first operator, it's clear what I mean, it's just this derivative operator here. While this operator here, I wrote it like this. So this is something that it wants to eat an element of a section of E, so it eats some v. And how does it eat it? Well, the v enters here, right? That's the meaning of stuff. Okay, so I regard this as an endomorphism which expects to eat a section and produce a section, and well, how does it do that? Well, the obvious way is insert the section here. Okay? And there's only one way to interpret this. But then what's happening in the last term is exactly the same thing, except I insert the v not in the argument, but I insert it here. Which is really the, if you regard this as an element of this, then in this first term, I insert the argument here, I contract it with this first thing. In this term, I contract it with the other thing, which means that I split them. And anyway, E star is the same as E because I have a variable. So you can think through if you want, but the point is that it's just, it's the transpose of this of that endomorphism. And the way I wrote it is that this thing acts on V. This is the operator I wrote. This is acting on sections of E, but in fact, it's perfectly well. I can just say that it acts on any section of because all these objects, I can lift the direction on any power here. I can use the connection to act on any tensor power. I can use an endomorphism to have an induced action on the higher power. Does this work on the functions? Does this work on n equals 0? Well, what do I have there? That should correspond to the fact that Lie derivative of a function is the same thing as this thing. So combining these two. So if I act on the functions, then I get it here, but endomorphisms act trivially on 0 powers. So this thing doesn't contribute. So this works, what I'm saying. The bottom line, sorry, it was a bit of a, maybe this deserves its own proposition, but you said that you can rewrite the Lie derivative in terms of connection like this. That's a useful formula by itself. Okay, and now let's just calculate value G and plus and minus index. So let me shorthand write this plus B. Okay, let me just call these two guys B. That's an endomorphism. It's not a derivative operator, it's really an algebraic tensor, an endomorphism. So how does such a thing act on G? Well, Lie derivative in general is a complicated object, but if I use this formula, then there is a derivative part and there is an algebraic part. Derivative part, how does this thing act on generalized metric? Zero, because this is a Levitsky thing. So I only have an algebraic action, which is kind of nice. So I have this tensor, then I have an algebraic action on my T. How does that look like following the standard conventions. This is a beta. So curly G is a two tensor, so there will be two terms. Bless you. Oh. Yeah, this is what I get.
So for this you only need the connection compatible with the metric, right? You don't really need to be also involved with respect to the sigma.
That's right, so I can arrange this, yes.
Okay.
But torsion freeness is needed.
Yes.
Thank you. Yes, so I can erase this here. Okay, so now remember that this. So G is a blow diagonal operator. It acts with identity or minus identity or plus or B plus and B minus, which means that this summation only I need to have both indices of the same dotted or undotted quality. So this first term, I really can replace this by B dot C dot, and this is BU and B dot. And same here, this thing has to be undotted. D. Oh, yeah. But this thing is just the Kronecker symbol. So what I'm saying is that this is BU. This is minus Kronecker because it's on B minus. So it's minus A C dot. And the second one, this is plus. So this is plus B U and C dot A. Okay, sorry for the lack of space. But now look, what is this B? So this B was an antisymmetric thing, right? Because it had DU with a minus and then a transpose. It's antisymmetric. So the fact that I can just say that this is one of them twice. So this is 2 times the second one. Can you still see this? Okay, and now what is this? Well, looking there, just translate what that means, and it means the following. So there is the first one with 2, and just following my conventions, this is the input, so it's this one, and then it's like this, and plus the other direction, 2. C dot U A, which is the end. That's what we were. Antisymmetrization. Antisymmetrization has one half. Okay. Anyway, now the exciting part. Is it okay if I go about like 3 minutes over time?
Yeah.
What about 30? Okay. Now, theorem. What you might call contractive or second contractive Bianchi identity. And you can use the same derivation in the ordinary geometric sense. If you haven't seen that one, you can try it. This one says for any Ricci beta connection, this is a succinct way to say that I have a current algebra with G sigma, and I pick D, Ricci beta. We have the following identity. And the second one, which is Okay, so there is a differential identity that connects Ricci and R and scalar curvature. And the proof is cool because it notices the following thing. So we have this Einstein-Hilbert function now. So this thing, because the way it's constructed, this is invariant under automorphism of the current algebraic. Under current algebraic automorphisms. This is one analog of the statement that Einstein-Hilbert action is invariant under diffeomorphisms. So, because this was constructed kind of in an it is invariant with the automorphism. So what does this mean? So, thus, if I, in particular, it's invariant under infinitesimal current algebroid automorphisms. And what are those? For instance, one is generated by the Lie derivative. So if I now change my metric by a Lie derivative, so the basic class of infinitesimal current algebroid automorphisms is given by bracketing or Lie derivatives with sections of the current algebroid. So I can this thing is invariant under that. So for any u, I have this generalized derivative. I can just deform my fields, but because the whole thing was invariant under these automorphisms, such a change should not change the metric. So that then the corresponding change here should be 0 because it was invariant. So now let's use our formula for this. We know how the general change looks like. It's a Lie derivative. Times the Ricci tensor. Okay, so remember the formula. Delta S was something that has Ricci times the change of the metric plus 2 times scalar curvature times sigma times the change of the Hall density. So this was the general formula. Now what can we do with this? So we can, first of all, we can use the formula we had there in the lemma to say that this is minus 4 this. And second of all, we can write this thing as, well, we have sigma, and we have 2. So that begs you to write it like this. Okay. So now we can use integration by parts in both terms. What happens in the second term? I just move the Lie derivative to the other guy. Right? What would happen here? I just move the derivative to the other guy. So how do I do this? In the first term, if I move d to the other thing, the sign flips, so I get 4. And I would have uc, and then I would have the covariant derivative of this guy, hitting these two guys, hitting Ricci and sigma. So if I move d from here to the other guys, then I have it hitting these two things, but sigma is invariant, so it's just hitting Ricci really. And sigma squared, I still need to antisymmetrize on these two things. Okay, that's how it was written here. Similarly in the second term, I can move it around and I get minus Lie derivative of r times sigma squared. And now I can profit because, okay, what do I have there? What is the Lie derivative of a function? It's simply that thing acting on functions. This is, if you want, this is the same as du on r. Which, if you want, if I want to split it into the dotted and undotted things, like let's say that this is ua dar plus uc dot bc dot r. And what do I have here? If I expand the antisymmetrization, this is 2 times uc dot dA Ricci AC dot minus 2 A BC dot Ricci AC dot. And then I just compare, and this is supposed to be 0 for any U. So I can just compare the terms, and the equality gives me the proposition. The U A part needs to be equal to this one, so this has to be equal to that, and this has to be equal to that. Cool, right? Unless I didn't mess up the coefficient, I hope not. So, just to finish, let me write down the one kind of obvious implication here. This thing.
So I guess you can even like prove it directly, right? Like checking the problem or not.
From what?
Like directly to prove it, is it possible?
Well, it should be, but I haven't done it, and it might be horrible actually. This is much easier. So this formula sometimes is called the Ricci-Pafuti relation. I don't know, does that name ring a bell to anyone? Okay. So this is the stringy name. It says that on a transit current algebra at least, the vanishing of Ricci implies the scalar curvature is constant. Okay? As I wrote it up, it's kind of obvious from it, right? Why is it so? If Ricci vanishes, left hand sides are 0, so the right hand sides are 0, which means that the covariant derivative of R in any direction needs to vanish. But the covariant derivative acts on a function by the anchor map. So you need that the anchor map is surjective to conclude, but anyway, that's the interesting case anyway. So this thing, so that's something similar to original geometry case is true. That if Ricci is vanishing, then R is not really 0, but it is constant. So physically, the physical interpretation is that I think this is where the name comes from. That if the beta functions for G and B are 0, then this implies that the beta function for the two atoms is constant. Okay, this is for experts. That if the beta functions for G and B vanish, the one for the atom is constant. And unless I'm mistaken, I think this you can identify them with the central charge of the corresponding signal.
Sorry, I'm a bit lost. What is that symbol? Beta
of these fields, G, B, and phi. This is beta functions of the.
Yeah, but phi is the
atom.
Okay.
Yes.
Yeah.
So in, let's say, the simplest bottom extent case, well, it is right. In the special case of exact current algebra, this is the implication.
And is the all loop relation? Or
This is one loop.
one loop.
Yeah, one loop. Well, actually, I don't. I mean, this Ricci is one loop particle.
Yes, but
this thing I don't know actually. Maybe do you know? Is it all?
No, I'm not just thinking.
That's a good question. Okay, one loop. One loop for sure, and the rest I don't know.
No, like the relation between the beta functions could very well be like an odd loop, but at one loop this implies that.
Yeah, that's for sure true. The one loop is this statement. I don't know if it holds true. Yeah, if it does, then maybe we should not call it this name. Maybe then it's a much weaker statement. But
but I don't know. I was just guessing.
So yeah, so this ends it for today, and so the next time I will try to do a little bit of the theory of the generalized Ricci flow, just to introduce what the so-called lambda functional, which, if I'm not mistaken, goes to Berolman maybe, and some sort of a little bit of playing with that and seeing that how one can get some interesting statements about Ricci flow, and then we end this part, and then we go to the next part. So thank you.